अच्छा, so we will start. Okay, we'll start and we'll start discussing just a quick brief recap of everything that we had done so far. Okay, so we had started discussing the new model for the atom, right? And we were looking at electrons, like how do electrons behave? Okay, so we did cover all of this. We discovered that electrons kind of their behavior is kind of they're difficult to locate, but you can demarcate a region in which there's a high probability of finding that electron, and that region is known as an orbital. And there were different types of orbitals. It was an s orbital, or you had a p orbital. If an electron was in a p orbital, then the electron would be buzzing around in this space on either side of the nucleus. P orbital was directional, so there were three types of p orbitals. The electron could either be buzzing around on this axis, or it could be buzzing around on the y-axis, or it could be buzzing around on the z-axis. So there were three types of p orbitals: px, py, and pz. And you have d orbitals. There were five types of d orbitals. If an electron was part of a d orbital, then it would be buzzing around in four lobes, located somewhere in those lobes. Difficult to really figure out where it is, but somewhere in that specific area, you'll find the electron. And the d orbital was also directional. The electron could exist in many different planes. And then you have f orbitals, which were seven f orbitals. So this is something that we did, and then we discussed this fact that every orbital can accommodate a maximum of 2 electrons. You can't have more than 2 electrons in a particular orbital. The 2 electrons, they repel each other, so technically they should not be in that orbital because they're going to repel each other. But the 2 electrons they don't just have a electric field, but they also have an accompanying magnetic field. And the magnetic field, it attracts. The magnetic field should be opposite. Only then, I mean, if one electron has a north pole, the other electron should have a south pole. So the magnetic field of the 2 electrons, it should attract. So there's going to be an electrostatic force of repulsion in an orbital, but at the same time there's going to be, because of the opposing magnetic dipole moment, that's the magnetic field, also referred to as opposing spins, the 2 electrons are going to attract each other, which is why the force of repulsion is going to get cancelled out by the force of attraction. And this is represented by two arrows. Like the s orbital, if it would be represented by a box. Every orbital can be represented by a box, and that box has 2 electrons. One arrow would be upwards, the other one would be downwards. That means upward spin, downward spin. That just means they're going to have opposite magnetic fields. Okay, is this part clear? Zaib, is this clear? Hania, is this clear? Anna?
Yes, sir.
Yes, sir.
Okay, so we did that, and then we started talking about subshells. Subshells were that the orbitals can be grouped together. An s subshell just had one s orbital. A p subshell had three orbitals, depending on directions: px, py, and pz. And since each orbital can have a maximum of 2 electrons, the subshell can have a total of 6 electrons. So the p subshell was this thing. This was one of your p orbitals, px, py, and pz. If you think of this as combined together, this is called a p subshell. If you group them together, if you group all the spaces together, that's called a p subshell. So it's a group of degenerate orbitals or orbitals that have the exact same energy level. So this is something that we did, and we talked about subshells, how many electrons can exist in a particular subshell. So you have electrons residing in all sorts of places. S orbital, a p subshell will have 3 p orbitals. A d subshell will have 5 different types of d orbitals. That leads to a total of 10 electrons. And an f subshell can accommodate, it's got 7 different f orbitals, and it can accommodate a maximum of 14 electrons because each orbital or each space would have a maximum of 2 electrons. So you had your subshells, and after that you had your shells. And this is what we started doing. We started doing shells. Now, shells wasn't a physical thing. it simply meant energy level. And as the shell numbers increase, they're also, I mean, this is also referred to as the principal quantum number. So as our shell numbers, they increased, the principal quantum number, and over here you can see that they are increasing. So what that basically meant was that if the shell numbers increased, that meant that energy levels were increasing. So our energy levels, they continue to increase if shell numbers increase. So every electron is going to have it's going to have a specific shell number depending on what the energy of the electron is. So here is how our orbitals are usually described. So for example, you have an electron is going to be stated. For example, if there is 2s and 1 written, okay, that's the notation that is going to be used for describing electrons. So we've got 2s1. What does that mean? It means that we have an electron in the s subshell, which just has one s orbital. This represents the number of electrons. And this 2 over here indicates the shell number or the energy level. Or we call it the principal. So we call it the principal quantum number. So you've got three things in the notation. That's the number of electrons. This is the subshell. This is the type of space that they're occupying, and the 2 indicates the energy level. So you can have 3p4. What that indicates is that that p indicates that there is p indicates that that's a p subshell. So there is a p. Subshell 4 indicates that that's the number of electrons in that particular subshell. And this 3 indicates the energy level, or the principal quantum number, or the shell number. So let's just write shell number. Okay, so that's a notation. And what happens with the shell numbers? That is something that has to be discussed. When we talk about shell numbers, what do we mean by shell numbers? It's the energy level. So for example, you have an electron in the first shell, 1s1. So 1 indicates that the electron is in the first shell. It has the lowest energy. You have an electron in an s subshell, but now it's in the second shell. And you have another electron that's in the s subshell, but the energy level is 3. So the shell number keeps on increasing. So this is shell number 1. This is shell number 2. And this is the same electron in shell number 3. What that indicates is, S indicates that the region the electron would occupy would be a spherical region. So this is going to be a spherical region around the nucleus. This over here is also going to be a sphere, and this over here would also be a sphere. But the region size would continuously increase. Why would it increase? Because the electron is becoming more and more energetic. So here's your nucleus. All of them, the S indicates a spherical region around the nucleus. So the electron is kind of buzzing around in this spherical region, somewhere in this region. So it's moving rapidly. I mean, this electron over here is moving rapidly in that particular area.
Sir?
Yes.
Aren't there meant to be 2 electrons in an orbital?
I mean, they're meant to be, but that's the maximum number. I mean, you can have one, you can have less than two. Is this clear?
Right. Yes.
Okay. So the maximum is two. I mean, you can have two electrons. Then it's going to be, if there are two electrons, then it's going to be called 3s2. And there would be two electrons in that particular area occupying that space, somewhere in that area. Uh, so you can have two electrons, that's the maximum number, but you can always have less than two. I say anyway, so we have these electrons. So let's assume we just have one electron. I'm just stating what happens when you have a higher shell number. A higher shell number means the electron is going to have more energy. It's going to be, remember, the shell indicates energy levels. A lower shell number indicates, so a shell is not a physical thing. It just represents whether the substance, whether the electron has less energy or whether it has more energy. So when it has less energy, then the electron is not that energetic. So it's going to stay very close to the nucleus. It would be buzzing around in that particular space, very, very close to the nucleus, because the nucleus would be attracting it. So lesser energy means that the electron would be found in places that are closer to the nucleus. That automatically means that the orbital is going to be smaller. And if the electron is in shell number 3, then that indicates that the electron is kind of very energetic. So the electron has a lot of energy and the electron is buzzing around and it's capable to go further away. It's able to overcome the attractive forces of the nucleus and it's able to travel much further away because it's more energetic. So electron would be found in places further away from the nucleus. Further away. So the region size would also increase. It's going to be a much bigger orbital. Okay, is this point clear to everyone?
Yes, sir.
Okay, so remember this. The shell is not a physical thing. It's as I said, the shell is not a physical thing. And just one second, let me leave a message. So the shell is not a physical thing; it just represents energy. So if something is at a higher energy level, the electron would be much further away. It would be much further away from the nucleus, much further away from the attractive forces of the nucleus. So coming back to this, every electron would be represented in this way. You're going to write the shell, whether it's the S or the P or the D or the F, which region it's occupying. How many electrons are occupying that region? And the 2 indicates, the number in front of it indicates the energy levels. Okay, is this clear? Anna, is this clear? Nabila, Alicia, is this clear?
Yes, sir.
Yes.
So we've figured out lots of things. We've figured out that electrons exist in shells, which have orbitals in them, and they occupy spaces around the nucleus. And we've figured out that each orbital can have a maximum of 2 electrons. And we also figured out that energy levels are given. So how to write the electronic configuration? How do we figure out where the electrons are? So now we're going to move to our main point, which is how to write or state electronic configurations. So around the nucleus, you've got many spaces around the nucleus where the electron could be present. So S, P, D, and F. And with different energy levels. So there's a table which is known as the Aufbau principle. Almost all atoms, all elements, they follow that table. And the table is like this. It's 1s, then you have 2s, then you have 3s, then you have 4s and 5s, and so on. Over here, there's going to be 2p, There's going to be 3p, then there's going to be 4p and 5p. Then you'll have the d subshells, 3d, 4d, 5d, and over here you're going to start with 4f, 5f, and it just continues. Usually you don't have that many big atoms, so that's your table. Now that table has all the subshells. That an atom, a nucleus, around the nucleus, it has all the different spaces, all the different regions around the nucleus. So how do you figure out how to fill the electrons? So electrons are going to be filled in this manner. So there's going to be, you draw these diagonals. And the diagonals, the different ways of making this table. So this is one of the ways. So all the diagonals are pointing downwards. And you just keep following those diagonals. For example, every atom, when you're trying to fill electrons, they're going to follow this principle. The first, you're going to follow the arrows from top to bottom. So the first subshell that needs to be filled is always the 1s. That means there's an s subshell in the first shell, which is the lowest energy level. Then there's going to be a 2s subshell, followed by a 2p and a 3s subshell. And after your 3s, there's going to be 3p and 4s. And after 4s, there's going to be 3d, 4p, 5s, and so on. So this is like this is what you're going to use to fill the electronic configuration. The electrons are going to be filled in this manner. You start off with the lowest energy levels, the first shell, all the orbitals in the first shell, then the second shell, then the third shell. The lowest energy levels are the ones that are going to be closest to the nucleus. So for example, I have a sodium atom and I want to write the electronic configuration of the sodium atom. But let's start with a small atom. So let's start with, and progressively we're going to try and figure out bigger and bigger atoms. So let's start with hydrogen. Hydrogen just has one electron, so it just has one electron. So, and remember, these are subshells. So there's going to be just one s, and that is going to have one electron in it. So what that means is that around the nucleus, there is going to be a spherical region around the nucleus, and there's going to be exactly one electron that would be buzzing around in that particular nucleus. And the other thing is that the electron would be very close to the nucleus. It's going to be a very, very small orbital. I can even sort of make it so I can make it smaller. Okay, that should do it. So the electron is not very energetic. It's the first shell electron, so it's going to be very close to the nucleus. Is this clear? Everyone, is this clear? Is it clear? Anna?
Yes.
I said, then you've got, then let's move to a bigger atom. Let's talk about something bigger. Let's talk about carbon. Now I have carbon, which has 6 electrons. Now 6 electrons would be that the first, the 1s will get filled up. 1s the s subshell can have a maximum of 2 electrons. That's it. I said, remember, this 2 is not, remember this, some people get confused. This 2 doesn't mean that they are 2s orbitals. It just means the energy level. There's 1s orbital with the energy level of the second shell, which means that it's more energetic compared to this one. I said, so after the 1s, there's 2s, and that can have a maximum of 2 electrons as well. And after 2s, you have the 2p subshell. Now the 2p subshell, how many electrons are we left with? We're left with just 2. So it's going to be 2p2. So that's my electronic configuration for this. And I can even try and draw this. What that means is, if I try to draw this, we will have a nucleus, and the first 2 electrons are residing very close to the nucleus. Low energy level, it's an s subshell. So there's going to be a spherical region around the nucleus. and there would be 2 electrons in that particular spherical area. So you've got 2 electrons in that spherical area. Then you have a 2s subshell. Now a 2s subshell will have a maximum of 2 electrons as well. Now what's the difference between 1s and 2s? The 2s would be bigger in size. The electrons in the 2s subshell are going to be much further away from the nucleus. So if I draw the 2s subshell, the 2s subshell will, the electrons, and let me draw this again. So the 2s electrons are going to be much further away. So these electrons would be occupying areas that would be much further away. Remember, the two regions would be overlapping. The first 2 electrons are occupying a spherical region very close to the nucleus. These 2 electrons are now occupying another spherical region, but that region is more energetic, which means that the electrons are now much further away from the nucleus and they're traveling much further away, but they're still occupying a spherical region. Is this point clear? Okay, is this clear?
Yes.
Okay. And then you've got a 2p subshell. So remember, all these regions are overlapping. The next one is the 2p subshell. Now here's a problem, and the problem is that the 2p subshell we discussed earlier was made up of 3 p orbitals. I mean, this is what we discussed somewhere over here. Even before that, I told you that a p subshell is actually made up of 3 separate p orbitals, px, py, and pz, all lying on different axes. So if an electron is in the px, then the electron would be on this area on this axis. So you've got 3 separate p orbitals now. So when I say that I have an electron in the 2p subshell, that means I have an electron, and there are 3 spaces: 2px, 2py, and 2pz. So the electron is in either one of them. So I'll draw the axis. So that's our axis, that's our y-axis, and let's say this over here is our z-axis. One second. Let's leave that. So I've got these x, y, and z axis. So when I say that a 2p subshell has 2 electrons, what that means is that there could be a double-shaped region over here, and there could be 2 electrons in that particular area, somewhere in that area. Or and remember, there are 3 different types of 2px, 2py, and 2pz. So there could be another region, and electrons could exist in that area. So there could be an electron that could be on the other axis, or there could be a third one where the electron could reside on the z-axis. So it would be buzzing around in these 2 lobes over here. So that is what 2p subshell means. 2p subshell means that 2 electrons, remember you've got 2 electrons. The 2 electrons could exist in any of the 3 orbitals. But remember how to fill a subshell. You've got 3 orbitals. Remember this, electrons in a subshell are always filled in a single manner first. So if you have 2 electrons over here, 1 electron would enter the 2px, 1 electron would enter the 2py. The third orbital would be empty. So there would be 1 electron that would be buzzing in this area. There would be another electron that would be buzzing in this area. The third of the lobes, I mean this space over here, this region over here would be empty. So is this clear that electrons in a subshell are always filled in a single manner first? And the logic behind that is that if I go back to the p subshell and we have a look at the p subshell, this one over here, you're going to have 2 electrons in this red area, you can have 2 electrons in the blue area, you can have 2 electrons in this area over here. Now, if I want to fill electrons, a maximum of 6 electrons can occupy this p subshell. But if I want to fill 3 electrons, then electrons usually tend to stay away from each other. So if one electron enters this, the other electron would occupy the other orbital. The third electron would occupy the third orbital. So they would always fill in a single manner first because they don't like each other. They all repel each other. So they would try to be as far away from each other as possible. So a p subshell is always, or any subshell would always be filled in a single manner first. Once they become half filled, then the second electrons, they start entering. So what that means is that when you're trying to fill a p subshell, so let's try and fill the 2p subshell. We just did that, 2 electrons. How would 2 electrons fill up? The p subshell has 3 different p orbitals. So one of them would go in the px, one of them would go in the py, the third one would be empty. If you have 3 electrons in the p subshell, then how would the orbitals look like? Your orbitals would be, you'll have 3 orbitals in the p subshell. And if you have 3 electrons, one would go in the px, one would go in the py, the third one would go in the pz. On the other hand, if you have 5 electrons in the p subshell, remember electrons would still be filled in a single manner first. The first thing would be 1 electron going and occupying each one of the orbitals, and then there are 2 electrons still remaining. Then another electron would come over here and another electron would fill up this orbital so that the orbitals get completely filled up. So is this clear? How to fill a subshell? Hani, is this clear? France, Anna?
Yes.
Yes,
Yes,
sir.
sir.
Achha, so the point, so always remember that the Aufbau principle, it's telling you the order of filling subshells. But how do you fill a subshell that's not completely filled? 2p2 means you've got 3 spaces, but only 2 of the spaces would be occupied. The third one would be empty. So let's do another one. Let's try and do an oxygen atom. How do you write the electronic configuration of an oxygen atom? It's going to be 8 electrons, so it's going to be 1s2, 2s2, and then you'll be left with 4 electrons. The 2p subshell can have a maximum of 6 electrons, so there would be 4 electrons in that. And if you want to figure out how do the orbitals look like, the 2p subshell has 3 different orbitals. And there's going to be 1 electron each. I mean, the first they're going to be filled up in a single manner, and then the 4th electron is going to fill up a p orbital completely. So let's try and do another one. Let's try and do sodium, which has 11 electrons. So remember, all these regions, they overlap. I mean, think of bees buzzing around some sweets. The paths that the bees are taking, they are overlapping. I mean, it's not that one bee is just buzzing over here and it's not allowing the other bees to enter that path. What's happening is an electron can be occupying a spherical region or existing. It would be moving around, buzzing around in a spherical region. But at the same time, there could be another electron which could be in a p orbital. So that would be buzzing around on this axis. But the two are not, I mean, they're going to stay away from each other. They're not going to bump into each other because electrons are negatively charged. So the electrons will find a way to actually kind of avoid each other. So the paths that the electrons are taking, or the spaces that the electrons are residing in, they are overlapping, but each electron maintains a unique path. For example, if I remove electrons from the 2s, then electrons, this spherical orbital would vanish. There would be nothing there. Previously, there was an electron that was buzzing around in this area. So if I remove those electrons, that particular space would be completely empty, or there wouldn't be any electron that would be roaming around occupying a spherical region. So coming back, let's try and write sodium's electronic configuration. That's going to be 1s2, 2s2, then it's going to be 2p6, Now the p orbital would be completely filled, and then you'll have 3s 1. How did I figure out the order? I figured out the order using the Aufbau principle, which is this one. 11 electrons, it's 1s2, 2s2, 2p6, and then there is 3s1. Let's try and write the electronic configuration of another atom. Let's talk about Cl. 17 electrons, so that's going to be 2 electrons, 2s2, 2p6. Then there's going to be 3s2. So I've filled all the orbitals, all the subshells up till this point. So that's a total of, I think, 12 electrons. What comes after 3s? You just go and have a look at the table. What comes after 3s? That's going to be 3p. So after 3s, there is 3p. And the 3p can have a maximum of 6 electrons. But over here, it will have a maximum of 5 electrons because you run out of electrons. You just have 17 electrons.
Sir,
Yes.
how do you know that 2p has 6 electrons?
We're talking about 2p subshell. We talked about 2p being made up of this over here. Remember, whenever you talk about the 2p subshell, like the p subshell, it has 3 different orbitals. It's a group of orbitals having the same energy level. There's going to be px, which is lying on the x-axis. So there could be 2 electrons over here. There would be py. I mean, this would be py. So there would be 2 electrons buzzing around in this space, and there would be pz, 2 electrons buzzing in this space. Hani, is this point clear?
Yes.
So, I mean, this entire thing is called a p subshell. We did discuss that. And the d subshell is, you combine all these spaces, that's a d subshell. The d subshell can have a maximum of 10 electrons. I did write this somewhere. So I've got an s subshell.
Yeah, I just understood.
Okay. So remember, which subshell can have how many? I mean, this has 3 orbitals, this has 5 orbitals, this has 7 orbitals. So according to this, that's the total number of electrons that they can occupy. Just 1 second. So we've done Cl. Let's do another electronic. All the electronic configurations are going to be kind of similar. Let's try and do what comes after Cl. Let's try and do scandium. Scandium is 23. So I think it's 21. Scandium has a total of 21 electrons. So that's going to be, I mean, it's going to follow the same 1s2, 2s2, 2p6. Then there's going to be 3s2. Then there's going to be 3p6. And that's a total of 18 electrons. We're still short of 3 electrons. We need to add 3 electrons. So what comes after 3p? So I'm going to have a look at the table. What comes after 3p? That's 4s, and then there is 3d. So after 3p, there's going to be 4s, and then there's going to be 3d. So there would be 2 electrons that would be going in the 4s, and there's just 1 left over here. Now the 3d can have a maximum of 10 electrons. This is the d subshell from the third shell. It can have a maximum of 10 electrons, but at the moment you just have 1 electron. That's it. So that's the electronic configuration of scandium. One thing that you should do is when you write the electronic configuration, I mean, it's better to actually just reorder them according to the shell numbers. Like the electron in the 4th shell would be the furthest or the farthest electron from the nucleus. It's going to be the most energetic. Okay, so once you've written down the electronic configuration following the table, just reorder them. The first shell electron would be closest to the nucleus because they have less energy. The second shell electrons would be much further away. The third would be even more energetic, and they would be even further away. And the 4th shell electron would be the farthest from the nucleus because it's the most energetic. So let's try and write iron now. So what's the electronic configuration of iron? That's I think it's 26. So it's going to be 1s2. Then you have 2s2, 2p6. Then you have 3s2, 3p6, and 4. I mean, the table 4s2 comes first, then followed by 3d. How many electrons are we left with? This is 20 up till this point. So this is going to be 6, I think. Once you've written down the electronic configuration according to the table, just try and reorder everything. Okay, so is this clear?
Yes. Yeah.
Okay, so just make sure this table must be on your fingertips. Now, the other nuances which we will study in a bit, but remember that I mean, you must know what the order is. You can either memorize this or you can just learn how to draw the table and just figure it out on your own. It's better to actually kind of memorize because you can't really waste. I mean, time is a huge issue in AS, in A levels. So make sure you just remember the order in which the subshells are going to be filled. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. I mean, you have to. It's better to just memorize all of this. Now, moving on, there's some the other ways of writing electronic configurations, but before that, we're going to study two special cases. That their electronic configurations are different. So you have to remember the electronic configurations of these I said two special cases. Number one is copper. Copper has 29 electrons. It's 29. So its electronic configuration follows the same Aufbau principle: 1s2, 2s2, 2p6, 3s2, then there is 3p6, and then you've got after 3p6 there is 4s2 in the table, and then there is only 9 electrons left. It's going to be 3d9. First thing, make sure that the order is correct. You follow the table and then you correct the order. Anyways, this is the electronic configuration. Now the difference is that the electronic configuration is not this for copper. There's a slight difference, and that difference is that instead of this being 3d9, it's actually 3d10. There are 10 electrons in the d subshell. Instead of there being 2 electrons in the 4s, there's actually just 1 electron in the 4s. So that's your actual electronic configuration of copper, which you have to remember. They give multiple reasons for that. A completely filled electronic configuration is more stable. So 3d9 is not preferred, but you just have to memorize that the electronic configuration of copper. You're not going to get the exact electronic configuration if you follow the table. You have to make this adjustment at the end. And the same thing happens for chromium as well. That chromium has 24 electrons. So the electronic configuration would be 1s2, 2s2, 2p6, 3s2, 3p6. Then there's going to be 4s2 or we can just write 4s2 later, because according to the table, the 4s fills first. So it's going to be 4s2, and then you'll have 4 electrons left. That's 24. So you have this electronic configuration, and even in this case, you have to make a little adjustment that it's not 3d4, it's actually 3d5, and this is not actually 4s2, it's actually 4s1. So you have to remember the two special cases, because if you follow the table, you're not going to get the exact electronic configurations. You have to make this adjustment right at the end. For copper, instead of being 3d9, it's actually 3d10. And this would actually be 4s1. And for chromium, instead of being 3d4, it's actually going to be 3d5. And this would be 4s1. Is this clear?
Yes.
So let's continue tomorrow then. just make sure, okay, most of you have probably studied this as well. But if you haven't, make sure you revise this. Okay, I'm sharing the link of the board as well over here. Just 1 second.
Sir, could you also please send the board of the equilibrium topic?
Sure, I'll send the board. Okay, sending both of them. Okay then, everyone, take care.
Allah Hafiz.